Okay, let's start with the first exercise. I think a very easy one. We covered cryptographic hash functions in the lecture. What are the two general properties of hash functions? What properties constitute cryptographic hash functions? Explain them in simple words. If you want to talk about that on stream, you just have to unmute yourself. But otherwise I will just answer it. It's not very difficult because it's just you can directly go into the lecture slides, take a look there. Not really hard, but basically what we have two general properties for regular hash functions. So the first one is that we have a compression, so an arbitrary input length, so it can be as large as you want, and you have a fixed output length. So and it's always this fixed output length, and no matter what you input, it will always stay the same length. The ease of computation is the second property. So if you have age and x, so the hash function and the value you wanna hash, then it's easy to compute the resulting hash. So no matter what data you put in there, there is no exponential complexity or something like that. And then you have cryptographic hash functions, and there are included some properties there in the solution of the exercise. I posted 4 in there, but basically you can describe them very easily. So pre-image resistance basically says that it's impossible to find the original X if only the hash of X is given. So you're not able to calculate X out of the hash of it. The second pre-image resistance is a little bit similar. So it's impossible to find a second X if X and the hash of X are given. And you want now to have two properties. So these two hashes need to be equal in terms of the output needs to be equal, but the input needs to be different. So you can take a look here. That's the definition here. So we have this second X. The hash of the second X needs to be equal to the first X without them being not identical here. Then the third property is collision resistance. It's impossible to find X and Y such that X and Y, the hashes of them are equal, but without them being identical. So also here collision resistance, very straightforward property. We also discussed last week a lot about the difference between collision resistance and secondary pre-image resistance. So I won't go further into that. And also the third property, hiding, when it's impossible to determine X in a hash, where it's basically salted with an additional value R, and this R is a random number, and yeah, so you can see also the solution here. We also upload the solutions online, so no worries about that. Okay, very good. Let's continue to the next one. The next question is a little bit harder. Alice wants to play rock, paper, scissors with Bob via an internet connection. So it's that one. And both want to win and are afraid their opponent will just wait for the message and respond accordingly, as no one knows when the other sent the message. Create a scheme in which it is not possible to cheat. So now it's again time for people from Zoom. Maybe you can share your screen. Maybe you can discuss a little bit about how you would solve this issue. Okay. Yeah. Yes, sure. So you're now on the stream and you can talk to all of them.
Okay, well then I have to mute the stream, otherwise I hear myself. Okay.
Yeah, it's always a good idea.
So my idea was that you can decode the decision of rock, paper, and scissor as a number. So 1 is rock, 2 is paper, 3 is scissors.
Okay.
And then you have a cryptographic hash function that is given. You can just choose that arbitrarily, and then you concatenate your decision, the rock, paper, or scissors, with a random hash, with a random number, like a large number that the other person doesn't know.
Yeah.
And you send the other person the result of the function. And when each person has sent the other person their hash, they reveal their decision and the random number, and the other person can check the decision.
Very good. So someone is complaining that the Zoom has a really severe echo. I don't think that's on me. I hope that's not on me. Because I don't know where this echo would come from. Sorry for that. Yeah, so coming back to your solution, that's exactly correct. So I'm going to display the solution on stream. So what we have here is we have a two-way, so a commitment scheme, a commit and reveal scheme. This is how this is called. And this is also what we do later on, for example, in Ethereum, when we basically want to create random numbers on the chain. So that works very well. So the commitment and reveal scheme works in two phases. We have the commitment phase. Both Alice and Bob commit themselves to either rock, papers, or scissors by hashing it with a random number. So what you propose in terms of putting 1, 2, 3 as the equivalent of rock, paper, scissors is fine. So you can also do something like that you basically just write it there as a string. And this commitment is sent to the other parties. And because the information is hashed and hidden basically with a large random number, there is no way for the other party to understand to which value or to which to either rock, paper, or scissors the other party has committed itself. And in the reveal phase, both parties basically receive the message from the other parties, and now they can reveal their choice and their random number. And they send basically this information to each other, and Bob and Alice verify if the received information matches the hash by calculating the commitment itself. And as of the properties of cryptographic hash functions, both parties are not able to change their initially committed rock, papers, or scissors. So the decision they made up front is not changeable anymore because of the cryptographic hash property. So you're not really able to change that because of the second pre-image resistance. So this looks in detail. So this is more or less a graphical display of that. So you have the secret X, you have the secret XB. So maybe I can zoom in a little bit on that. And maybe I can make it a little bit sharper. That looks good. And so we have the random number RA, RB, and we have our commitment. Our commitment is basically calculated here and here. And these commitments are now sent to each other. And after the first phase, both parties know the commitment of the other party. And now they say, okay, we now reveal our R, our random number, and our decision. So, check if it's actually the correct result, and then they can calculate basically the winner. Also, it is irrelevant which party was first, it's also not important. So the order of the sendings of the messages here is not important. But it's in general, this is an example to say, okay, how could work this on chain, and how would you do something like that? Okay. We have some questions. Let's take a look at them. Are there other schemes that we have to know and use? So we introduced them in the exercise, and we also will cover some of these schemes in other lectures. So this is just like a little bit of a pre-example, but we will introduce the most of them, or all of them we know, and so that's definitely you don't need to know more than that, but could be some case that we use some of these schemes, we fiddle around with them, so understand the properties, you know how to use them. That's important. For Q2, could they send each other their choices in an encrypted file and then tell each other the key later? It is probably not the answer you're looking for, but what do you give points to such an answer? So that's obviously a correct answer, because you can also basically encrypt data and later on reveal the key. But in the idea here is really to use what we introduced in the lecture. So we did not use encryption. We did not talked about that. So it would be correct. And in the exam, it would be okay. Use the information suggested in the lecture, or it is suggested to use the information in lecture. But obviously, if you are not totally off limits, and if you are fine, and it seems that you understood the problem and the question, then this would obviously lead to points. And also a question from a more advanced user: do atomic swaps work the same as commit and reveal? So their commit and reveal uses some scheme like that. So a lot of these advanced technologies like Lightning Network, like these atomic swaps or cross-chain swap, stuff like that, often use something like that. So that's actually the case, yeah. But these are advanced technologies or advanced protocols we do not introduce in this lecture. Okay, let's continue to the next exercise. A fairly interesting one. Not too many people also wanted to talk about that. It is best practice to store only hashed user login information. Often the hash not only contains the password itself, but also some additional user-specific information. Explain why this is a better approach than just storing user passwords. So any idea from Zoom, or I can just go ahead? Okay, no one raises their voice, and not too important. So let's go into that a little bit. It's actually very easy. So when you think about websites, so websites might get hacked sometimes. So if you, for example, use WordPress or something like that, it's always it's a little bit dangerous, because it's just such a popular framework, for example, and a lot of backdoors, a lot of hacks get out there, and they could hack web pages. So hackers breach into this website and obtain a database. And in this database, often user information is in there, email addresses, passwords, stuff like that. And you want to protect your users. You want to protect the passwords of your users, because that's a very, very good source for income on the black market if you can sell email addresses with associated passwords. So there are quite interesting statistics out there that a lot of passwords are reused, and even reused for services like PayPal or so, where really financial systems are included. So that's very important. And so you want to make it as hard as possible for the attacker to obtain the actual password of the user. So you hash the password, but you do not only hash the password, but you hash it with a salt. So you add something to the password such that it's very hard to obtain the password from the user. And often it's a user-specific information. So you take, for example, you have an additional a row, a column in your database, and this database basically contains like a random string, and concatenated with the password, this is hashed and then checked, so that it's very hard to revert the password from the hash. So that's a very good approach, and if you do that, it's better than just hashing the passwords because on its own. Because if you do that, then people take lookup tables, so they basically have the top 1 million used passwords already hashed and check it in your database. So that's what is also here. I also linked to the OVASP password storage cheat sheet. So these are the experts on that topic. They really understand, they really know what's going on there and how you best should implement that. So I'm not an expert for this, but that's just for you to have a little bit of an understanding what we could do with hashes. Okay, so let's continue to the next question, and this is, I think, is where I would really like to see some of you guys of your code, because that could be interesting, I think. So the exercises now about search puzzles. We want to create a search puzzle, use the puzzle ID BBSE E01 and the SHA-256 hash function, assume D to be 000F00. A, what is the value that solves the puzzle? How long does your computer execute until it finds a result? Select your favorite programming language and develop this search puzzle. So anyone on Zoom wants to share the screen, wants to talk a little bit about their solution. Otherwise, I'm going to talk a little bit about mine. Yeah, sure. I'll put you on the stream and you can talk. Go ahead.
I can share my screen, I think.
Yeah, you should be allowed to do that.
Not yet. It says cannot share screen while other participants sharing.
Okay, then I need to. So now you should be able to do that.
So in my solution, I basically use some of the information from the slide.
1 second, I'll share the.
I use the puzzle ID and I just use the hash.
Can you zoom a little bit on that? Because I only see the window, it's quite small. Do it like this. No. Sorry, there's a little bit of technical issues here. So now it works. Continue.
So I use the puzzle ID and the hash lib function from Python. And I just compute the hex digest and just try to find the first value that's lower than the provided D. I just
How did you compare, or how did you
so I split it based on the first 7 digits.
okay. And you treated the string as hexadecimal and compared it to the D.
Yes.
Yeah, very good. And what is your result?
I think you can see it just below the code. It's basically it took the value of x is 99,871.
Okay.
It took 0.81 seconds.
That's interesting because I found another number
And
there.
the hash is the hash you can see is
Yeah. It's quite so that's definitely a correct solution. I have a different solution, and I think the reason for that is because in your you say you encode the puzzle ID as UTF-8, and I'm not sure how that turns out in the you did not, you used a blank instead of a underline in the puzzle ID. That could be the case. That could be the reason for it. But I have so it's correctly programmed, and you did it actually right. I hoped for someone for a small mistake, but I will show you a common mistake, or we'll talk a little bit about that. But that seems very good. I also will show my source code in a second. Okay, thank you very much. Let's turn this off. Very good. Okay. So what I have is I'll share my solution here, and this is my console here. So I will walk you through that so that you get an understanding of what is going on there. I have to find my and there it is. Exactly. So we have our so I program in PHP. You might wonder what is wrong with this guy, and that's the first programming language I learned in my life. So that's also I spent the most time with, and therefore it's the easiest to do it for me. But you can do it with every other language as well. So no harm there. So what you see here is obviously we set the error reporting to 0, so that's very important. If you're a real programmer, just disable the errors and everything works fine. I defined the puzzle ID, so BBSE /E01. I defined the difficulty D, so 4 zeros. I defined X starting with a 0, and I have a while true loop, which basically does following. So we calculate the hash. So we use SHA-256 of this thing. So we take the puzzle ID, in this case BBSE E01, and the X. So the X is here, like this one, and this concatenated is hashed. And now we do some cruel, it's really cruel, comparison. So what we do is, your student did it correctly because he took the number, interpreted as the hash interpreted as a hexadecimal number, and took that as a comparison. I made it a little easier for myself because I said, okay, I don't care about hexadecimal here right now. And I just want to look if the first 4 characters start with a 0, because that's what we need here. And what we do is we generate a substring out of this result, starting from character 0 for the length of our difficulty. So this string length basically returns 4. So it's also, if I would write here 4, it's the same result. And I check if basically the first 4 characters of our result here is equal to D. And if that's the case, then I say, okay, I define the variable res as x so that I know, okay, what's going on there, and I break. And then I can say, okay, after that found x, our x is returns the hash value like this and that. And I can do it now here. So if I take a look, it's only the index PHP, and now I can do PHP index PHP, and it generates for me 7852, and with that hash value. So I don't know how many of you tried it, but that should be the solution for the exercise here. I did not try how long my computer takes, because it really depends on your machine. So and also where you use it. So this is a so-called Windows subsystem for Linux. So on my Windows machine, this is like a small Linux machine where I can do all the fancy stuff. People start asking why I did not do it with Solidity. Very good question. Solidity is the programming language for Ethereum, and Solidity is not made for compute-intensive work. So it's a software or it's a programming language which is used for on-chain calculations, and each of these nodes in the network basically have to compute all these steps on their own. So I do it locally on my machine. I don't have to run it in Solidity. I think it would work, it could work, but Solidity is such a slow language, such an imperformant language. So really don't use it for any heavy computation. Just use it for what you really need to do on chain. But that's a story for another day. Okay, let's look back at the exercise. So we can take a look at the solution. That's the code here. And that's the result here, 7,852. That's the result here, and further information about this program. So this is how PHP basically allows you to concatenate numbers, stuff like that. So the puzzle ID with X is concatenated just by a dot. In JavaScript, for example, you would use a plus. So, but that's totally up to your programming language. So maybe let's talk about let's talk a little bit about what the downside here is with my approach, because I think it's a little bit it's my solution sometimes gives a little bit of a simplified idea of what's going on. Sorry guys, I need to share my screen. So now it works. iPad Zoom, very good. Okay, so the problem here is that if we look at these, if what I do is we want a hash which starts with 4 zeros. And what I do is basically I can only allow for this hash if it has to begin with something like 4 zeros, 5 zeros. And it actually does not matter if we say it should start like that, or it should start like it is always So the difficulty here between that and that is different, but between these two, it's equivalent. And if you just look at the strings here, or at the beginning of the hash, then it's not totally correct, because now if you would do it like that, you can only increase the difficulty and reduce the difficulty by the factor of 16. So if you would say, okay, now we have now we want to find 4 zeros, and then we want to find 5 zeros. So now that some kind of takes an amount of I don't know what, but that takes of this we don't know what times 16, because this additional number has to be found there. And so it's really important, or for Bitcoin or for blockchain, it's really important that we say, okay, we need to have something like below or equal to 0, 0, 0, and then, for example, 1, 5, 6. And then with that approach, like really saying, like your colleague did it very good, to say, okay, we need to treat it as a hexadecimal number, and we really need to make a comparison between these two numbers. If you just say, okay, the first 4 characters here are relevant, or the leading zeros are relevant, then you reducing that to only these times 16s, or divided by 16 difficulty, and that's not really useful in terms of blockchain, because you will see later on the reason why. Okay, let's continue, because time. Exactly. So I'm going a little bit over this now. I think then we focus a little bit on the last parts. And so 3 computers, hashing power 50%, 30%, 20%, overall 100,000 hashes per second, participate in the search puzzle. All computers iterate through all the x with x plus 1, so like we do here. X is x plus 1. Which one wins the search puzzle? So obviously the computer A wins, as he will reach the solution we calculated beforehand as the third computer. It is the fastest one, so that's for sure the point here. Is there a way for the losing computers to increase their chances of winning? So that's a very good question. Can other computers maybe win in terms of like their hashing power? So the idea is here that we can increase the chances of the losing computers by not iterating through this by x is equal to x plus 1, but by selecting x randomly. And this is for the reason of the cryptographic hash function, because they the result of them is the resulting hash function is like randomly distributed all over the output space. So we cannot compute it. We cannot how would you say it? We do not know the outcoming hash before we actually calculated it. So taking randomly out of x, so assigning random values to x, can be a better approach than increasing from x plus to the next number, because then you have a better chance. So you can try it out yourself to take a rand here, and then it's much more easier to win this race. And if you simulate this yourself, which we don't have time for, you will see that in the long run, A wins with 50%, B wins with 30%, and C wins with 20%. Can we design the puzzle in such a way that the users win in accordance to their hashing power? So now it's not the user who's responsible for that, but it's the game designer, so to say. And we can do that. It's not that difficult, because we just introduce an additional variable into that. So we had the puzzle ID, we had the x, And now we can attribute a user-specific variable in there. For example, the ID or the name of the player. And when we do that, they can go back to iterating by adding +1 to x, and it will remain fair. So we introduce a variable in the puzzle ID that is user dependent. For example, the hashing process could look like this. So the puzzle ID still remains in there, but we add the computer name. And as this computer name is for every participant different, this results in different hashes all the time. Okay, let's take a look at the Merkle trees here. We have these 4 data elements. So this is the Merkle tree we saw in the lecture. And I'm trying to, okay. And it contains 4 data elements. How would you create a Merkle tree with 5 elements building upon the given structure? So the solution basically can be very different. So I have to say, and that's also what a lot of people asked last session. And there are many ways how you would do that, but I want to give you a little bit of an idea about that here. So let's take a look, because we have now, instead of 4 elements, we have 5 elements. So let's do it like that. We have 1, 2, 3, 4, 5 elements. So as you know, we do hash here, we do hash here, we do hash here, and we do hash here, and we do a hash here. And that is fine. And now we need to connect, we need to concatenate hashes. So let's name them hash 1, hash 2, 3, 4, and 5. So what we do here is we create a new hash here, and this hash is hash 1 concatenated with hash 2. This is also here, hash 3 and hash 4. And now we approach this one here, this on the right. And that's a good question, because there could be a lot of solutions in terms of, okay, we do like something like this, and now let's introduce that in here somehow. So that would work, but that's not really the official way. So I want to tell you how it's done in Bitcoin, because I think it's easier in terms of, okay, we want to do some kind of inclusion proofs. We want to do that. Then it's really equal for all data elements. If you don't do that, you have a little bit of problem about that. So how Bitcoin does it in this case, if there is an element missing here, and that's currently the case, then it just replicates the element. So what it does here is like, okay, let's just put h5 again there and do this as we did before. So now we have as hash from hash 5 concatenated with hash 5. So now we can continue the same. So this is again, like this is, that's hash 1, 2, call it like that. That's hash 3, 4. And we hash 1, 2 concatenated with hash 3, 4. And then we have this one covered. And then again, we approach this here. So we now don't know how to handle this one. And this is exactly what we did again now. So this is replicated, this hash 5, 5 is again replicated to hash 5, 5. And we do the same here. So we concatenate again the hash 5, 5 with the hash 5, 5. And now we can calculate that. And now finally we have 2 elements left, and now we can calculate this root hash. Again, by concatenating this hash and this hash. So that one and that one. And so that's how you would add a 5th element in there. Also note that basically you can look here at the so this one is our original tree, and this is basically the second half of it, and this is the result because we had some kind of an overflow. We have 4 elements there, which equals to 3 layers, so 1, 2, 3. But if we include more than that, then suddenly a layer 0 arises. So that's the key point here. Okay, so let's continue here. Let's get back to our solution. And this is exactly what we see here. So this is a little bit another display as I did it. But basically what we do is we duplicate the hash. If there is some element missing, we duplicate it there. And also, that's a very important remark here, do not recalculate Merkle trees. So in blockchain, you insert Merkle trees, and as the blockchain data structure is immutable by itself, that's very important that new trees are always added and never changed. Okay. So the technical university, we have a little bit of timing issues. Sorry, I spent too much time on the first part. And so the let's take a look at this question here. So the Technical University of Munich offers a service for companies and other interested parties to validate certificates it has issued. Therefore, the administration decided to hand out a PDF document to each student with his or her diploma and publish all hashes of these diplomas on certificates.tum.de. This website provides an easy way for anyone to validate the document. So if a student wants to prove she or he got the certificate of TUM, she gives the PDF document to the company. The company hashes the file and verifies that this hash is indeed published at certificates.tum.de. A. The administration decides that it might not be the best idea to just publish all hashes, as it reveals the number of diplomas issued in a certain time period. Design a process using hashing algorithms such that the integrity of the diplomas is still ensured. It is unknown to a third party how much diplomas are issued, and the administration still wants to publish some information, e.g. a database in the back end with a front end. Should not be used. Explain what additional information is required to properly validate a certificate. So that's the basic idea here is to say, okay, as we introduced it in the lecture, we want to use Merkle trees. So we saw that beforehand, how we set up a Merkle tree, how this data structure looks like. And what we can do now is we can also create for the TUM a Merkle tree. So for example, the semester ends and 200 people graduated, and then all these hashes of these 200 documents can be stored in one single Merkle tree. And this hash, the root hash of the Merkle tree, can be published to these certificates.tum.de. But unfortunately, you need some additional information if you want to use a Merkle tree. And that is basically the membership proof. So as you remember from the PowerPoint slides, let me see if I have them here. Yes, I have them here. If you remember this slide, you basically need to provide this information alongside the certificate, such that a student can prove that his hash of his PDF document is actually included in the root of this Merkle tree. So that's also described here, and obviously, so that is the solution, and this is just a remark in terms of, okay, this is not a real-world example, or this is not an example that we would expect to work that way, but it's rather for you to get a little bit of feeling for Merkle trees. Okay. The administration wants to extend the tool such that it is possible to invalidate hashes. It discusses if it should just publish the revoked hashes. However, this would reveal the number of certificates it has revoked. First, explain why it is not possible to remove a hash out of a Merkle tree. Further, explain why storing additional Merkle trees with revoked hashes still allows students with revoked certificates to validate their certificates. The solution is quite simple. So explain why it is not possible to remove a hash out of a Merkle tree. So in theory, it is possible because you can recalculate the Merkle tree and republish it, but this is not good. Why? Because in that case, if you remove, if you would remove a hash of a Merkle tree, then all this information which has been sent out to the other students, their proof of membership information, would become invalid. So that's the key point here. If you remove hashes from there, then all the other information becomes invalid and you would need to resend them. And that's obviously not really a good way to send students like, okay, yeah, we updated our Merkle tree, please see new information here. Further, explain why storing additional Merkle trees with revoked hashes still allows students with revoked certificates to validate their certificates. So this is also a interesting point. If you would basically also publish Merkle trees with revoked certificates, then there is a downside to that, or it would not work. Why? Because you would have to provide this proof of membership to the student who has his certificate revoked. So this student could just omit this information, say, okay, I'm not giving this out to another party, and the third party would have no way to check if it's actually in the Merkle tree or not. So that's the reason why we cannot use Merkle trees for revocation purposes here. And that's also in here. Explain why using Bloom filters is not suitable for validating certificates. So that's the membership question again. Bloom filters would be a very nice idea, but as I told you beforehand, the Bloom filters itself are not suitable because it is very easy to generate false positives, or it's likely that false positives occur, and with that you could basically fake certificates, and that would be not a very good way. Yeah. Okay, let's move to the last question, and the last question is about public keys of identities, and we also covered this in the lecture, so that's not too important there, but why are public keys of identities hashed before they are used as an address? Name two reasons and explain. And there are two reasons exactly put in the slides. So the first reason is because the public keys are rather long, and hashes basically reduce these public key sizes to a more to a more easy handleable way. And also it's because of the quantum resistance. So if quantum computers are feasible, the signature schemes you currently used will be broken. And to prevent this generation of private keys out of public keys, you can hash this public key and use that one. And if you don't reuse a public key twice, then you will still be able to hold onto your Bitcoin, for example. So that's a second reason here. And yeah, that's about the exercise sheet. So I'm really sorry about rushing through this because we now have 7 minutes left for the exercise sheet, and I have actually no time for the lecture recap, which I'm a little bit sorry about, but we have to see how this works out in the future.